This is Practice Exam 3. This is covering the chapters on confidence intervals, estimating a parameter, hypothesis testing for both one population and for two populations. Okay. First question is asked to express a confidence interval of 0.491 plus or minus 0.057. Well, in this format. Okay. And we know that this is the point estimate and E is the margin of error. So the other way to express that is you have your point estimate for proportion, which is p hat plus or minus your margin of error. So if we were to do that here, our proportion is bounded between our point estimate for this proportion, which is our sample proportion, minus the margin of error, and our sample proportion plus the margin of error. We have 0.491 minus 0.057 and 0.491 plus 0.057. If you were to subtract these and add them, you would get 0.434 and 0.548. So in our case, that's answer choice D. Second question here. The following confidence interval is obtained for the population proportion. That's the confidence interval here. Use these confidence intervals to find the margin of error E. Okay. Now, there is a formula for the margin of error because of the fact that we have our lower bound and our upper bound, right? And at the center, you're always going to have your sample proportion, right? Right. And this distance here is the margin of error. This distance here is also the margin of error. So over here we have p hat minus E, and this is p hat plus E, right? That's what the lower bound and upper bounds are. Correct? So in order to get the margin of error, the formula for that from the notes is your upper bound minus your lower bound over 2. So in our case, this is our lower bound, this is our upper bound. So we have 0.752 minus 0.724. And if you were to divide those, subtract those and divide those, you would get 0.014. Okay. And that's answer choice D also. Now as a bonus, if you actually wanted to find, let me just write this here as a bonus. If we were looking for p hat, the point estimate is at the very center of this interval, right? So it's going to be essentially the mid-range, or you just add up the lower bound and upper bound, divide by 2. So in this case, it'll be 0.724 plus 0.752 over 2, and you would get, running out of room here, you would get something like 0.738. Number 3. A private opinion poll is conducted for a politician to determine what proportion of the population favors adding more national parks. How large of a sample is needed in order to be 95% confident that the sample proportion will not differ from the true proportion by more than 4%? Okay, so they're asking for how large of a sample size that we need. Okay, so in this case, since we're dealing with proportions, right, we're going to use one of those formulas, right? There's 2 versions of this. One of the versions requires us to know a prior estimate for the true proportion. And if you don't actually have a prior estimate for the true proportion, then we use the other version of the formula. Okay, and if you recall, the formula is this. Okay, so n is our sample size, P is a true proportion, or maybe a proportion from a prior study. Z is our z-score, a critical value. You will have to look that up depending on what type of confidence interval we have. Okay, and then E is the margin of error. Okay, so if P is unknown, we're going to replace this P times 1 minus P by 0.25. Essentially, P is going to be 0.5, so 0.5 times 0.5 will be 0.25. Okay, if we did actually have a known prior estimate for P, then we would actually plug that in. Okay, so that means we need to know what Z alpha over 2, our critical value, and our margin of error. Okay, the margin of error, they told us that they don't want this to be more than 4% from the true value. So you want that, essentially you want that window to be plus or minus 4%. So that's our margin of error. Our z-score, well, this comes from just looking it up from the tables, right? And this is for a 95% confidence level. This value is 1.960. The most common mistake here is to forget to square this fraction. Okay. If we run that through our calculator, we get 600.25, and we always want to round up. Because if we round down, then we won't actually meet all the criteria required, like 95% confident or within a 4% margin of error. Okay, so if we just round up to the next whole number, then we'll make sure that we achieve those parameters there. 601. That's B. Number 4. Use a given degree of confidence and sample data to construct a confidence interval for the population proportion P. Of 380 randomly selected medical students, 21 said that they plan to work in rural communities. Find a 95% confidence interval for the true proportion of all medical students who plan to work in rural communities. All right, so this was just a sample of 380 medical students, and of this sample, 21 of them said that they'll plan to work in a rural community. Now, we actually want to see what the true answer is, and we want to have a range or a confidence interval, and we want to be 95% confident that it's within that interval. Now, since this is a multiple choice question here, we can just go straight ahead and use the 1 prop z interval, right? Because we're dealing with proportions, right? Just by the multiple choice here, we know that we're dealing with proportions here. And they also talked about that in the question. We need the inputs. We need x, we need an n, and we also need to know what our confidence level is. Okay. Our sample size was 380. There were 21 that planned to work in rural communities, and we want a 95% confidence level. So that's what we're going to put into our calculator. Again, if you run that through your calculator, we're going to get something like this. Your lower bound will come out to be 0.0323, and I'm rounding to make sure that it matches up with one of our answers here, because they're all rounded to 4 decimal places. And our upper bound is 0.0782. And this answer is C. Number 5. How many women must be randomly selected to estimate the mean weight of women in one age group? We want 90% confidence that the sample mean is within 3.4 pounds of the population mean, and the population standard deviation is known to be 25 pounds. Okay. So again, they're asking to find a minimum sample size. How many women must be randomly selected? And we're dealing with mean weights, right? So the formula for this would be n equals sigma times the critical value over the margin of error, the quantity squared. Again, where this formula comes from, if you recall from the previous lectures, is just the formula for the margin of error and just solved for n. Okay. Now this particular type of problem requires us to know a prior estimate for the standard deviation, even though we haven't actually conducted the analysis on this sample. We do have to have some sort of idea about how spread out this data is from some prior estimate. Right? So do they give us everything that we need? Well, they give us sigma. Do they give us a critical value? And then the margin of error. All right, they do tell us that the margin of error, we'll have to look for that keyword within 3.4. The standard deviation, they say it's known to be 25 pounds. And then for the critical value, you have to get one that corresponds to a 90% confidence interval. So a 90% confidence interval corresponds to what? If we look that up on a table, that's a 1.645. If we run those numbers in your calculator in this formula, and then don't forget to square this, you're going to get 146.3. Again, we always want to round up to 147. Number 6, 30 randomly selected students took the calculus final. If the sample mean was 95 and the standard deviation was 6.6, construct the 99% confidence interval for the mean score of all students. Okay, so this was a sample of 30, right? And we had a sample mean of 95 and a sample standard deviation of 6.6. And we're looking for a 99% confidence interval. Okay, so for a confidence interval on a mean score. Confidence interval on a mean score, right? We have to have our lower bound and upper bound. We're going to be using a thing called t-interval. Okay, the inputs for the t-interval on your calculator are going to be x bar, s, n, confidence level. They did tell us our sample mean was 95, sample standard deviation was 6.6, sample size was 30, and the confidence level was 0.99. Okay. If we run this through t-interval on your calculator, then we get 91.68 as our lower bound and 98.32 as our upper bound. Okay, and make sure you round to 2 decimal places, that way it matches up with the multiple choice answer. And in this case, we get answer choice C. Number 7. The mean replacement time for a random sample of 20 washing machines is 10.9 years, and the standard deviation is 2.7 years. Construct a 99% confidence interval for the standard deviation, sigma, of the replacement times of all washing machines of this type. Okay, they're asking for a confidence interval, 99% confidence interval on a standard deviation sigma. Okay. Now to find confidence intervals for standard deviations, we do have a formula. Now our calculator does not have this formula in it natively. But if we get all the individual pieces here, then we should be able to calculate this. Now, for this confidence interval, we're going to need to know what S is, we need to know what N is, and we also need to know these chi-squared critical values for left and right. Now, I don't use tables to come up with these numbers, even though it's very easy to come up with these values using tables. We'll use technology. Okay. Now, you can either use Math 200B in your calculator if you have that program. Otherwise, you'd have to use some sort of online solution, maybe an online calculator, which I'll show you how to use. So in our case, the sample standard deviation is 2.7 years, and the sample size was 20. Sometimes they throw you off and try to give you the mean. Well, in this case, they did the mean, which is 10.9 years, and that's unnecessary, not needed. Why is it not needed? Because the formula here doesn't require the mean at all, right? Because we're only measuring the spread of our data. Okay, let's go on to an online calculator and see what we need. Okay, graph pad. I just chose a website that has these calculators for you. There's many websites. You can use different ones. Just make sure you know how to use them correctly. This one has ways to come up with the confidence interval for certain parameters. This one says CI of a mean, difference, standard deviation, right? So that's the one we're going to choose here. And I'll have a link to this formula in the description of this video. We're looking for the confidence interval for a standard deviation. So that's that option. Continue. And they do give us different ways to input our data. If you have a whole list of data, you can put up to 50 values here. We weren't given a list. We're actually just given the standard deviation and the sample size. So we're just going to use that fourth option here. Our standard deviation was 2.7. And the sample size that we had was 20. Now the only limitation to this calculator is that you can't specify the desired confidence level. Okay. If you calculate now, you get essentially three options: 90%, 95, and 99. And if it's not any one of these, then you would have to actually come up with those critical values using a different one of these calculators. But in our case, we wanted a 99% confidence interval. So our answer is going to be this. Okay, 1.895 to 4.499. I believe the answer choices in the multiple choice were only one decimal place. So this would be what, 1.9, and this would be 4.5. So let's go back. We get 1.9 and 4.5, which is answer choice D. Now, if you had something other than the 99% confidence interval, and let's actually go through the exercise here. Then you can actually come up with the chi-squared left and chi-squared right. So you want to draw a picture to kind of get an idea of what's going on here. Here's 0, chi-squared left, chi-squared right. We want a 99% confidence interval, so that means this middle portion is 0.99. And what's left over? Well, 1%, right? And half of 1% would be 0.005. And the other half of that 1% would be 0.005. And in order to come up with these two critical values here, we have to use that calculator on GraphPad. So let's go to that. Now we're back at this calculator here. I'm going to go to where it says choose a category. And in this case, I'm going to calculate a chi-squared here. It'll be this third option here. I need to come up with a chi-squared. So it's going to be the second option on the calculator. Calculate a ZTF or chi-squared from a probability. And for us, we're looking for chi-squared. So the probabilities here are in reference to the right side of the specified number. So if I'm looking for the left one, it'll be 99% plus 0.5%, which would be 0.995. And the degrees of freedom is your sample size minus 1. In our case, our sample size was 20. So our sample size minus 1 would be 19. And we'd compute that. And we get 6.844. So I'll copy that over. And we'll do the same thing for the right side. The area to the right of that would be 0.005. So we'll go ahead and put that into the calculator. So from here, let's go back to enter our data. Change this to 0.005. Same degrees of freedom. Compute chi-squared. And we get 38.582. 38.582. So of course you can put this in. This is obviously the longer way to do it. And if you have a 99, 95, or a 90% confidence interval, then I would prefer the previous way. We have 19. If you calculate this, we get the same thing as we had before. If we round to one decimal place, we get 1.9 and 4.5. Same thing. Okay, so that was all the problems on the chapter on confidence intervals and estimating a parameter. The next questions are going to be on hypothesis testing for one population parameter. And then after that, we'll go into two population parameters. Okay, question number 8. According to a recent poll, 53% of Americans would vote for the incumbent president. If a random sample of 100 people results in 45% who would vote for the incumbent, test the claim that the actual percentage is 53%. Use a 10% significance level. Okay, so in these types of questions, you always want to be able to identify the claim statement since they're asking us to test a claim. And what is that claim statement? That the actual percentage is 53%. Americans who would vote for the incumbent president is 53%. All right, so let's go ahead and start where we always start here. Step 1 is the null hypothesis and the alternative. What parameter are we talking about? Are we talking about a proportion, a mean, a standard deviation? And there's usually keywords that indicate that. Okay, so for us, the keyword here is percentage. That would be a proportion. Another keyword for proportion would be rate. Okay, there could be others too. So we're talking about proportion, so that's the symbol for proportion. And the null hypothesis is always a statement of equality. And if we read the claim statement, the actual percentage is 53%. So in this case, the claim is that it's 53%, so that's 0.53. That is the claim statement. So what would be the alternative? Well, the opposite of equals is not equal. And again, these two numbers have to match up. So in this case, the null hypothesis is the claim. Step 2 is our significance level. They told us that it's 10%. Step 3 is our test step. For proportions, the test stat is a z-score. And the formula for that is p hat minus p over square root of p times 1 minus p all over n. Again, the pieces of this equation are what we need. This comes from data. This comes from the null hypothesis. The p is the same. P is up here. The n is our sample size. So let's go ahead and list out what we have here. So we have p hat, which p hat is equal to x over n, right? That's our sample proportion. So that means we need to know what x is and also what n is. So again, the p comes from the null hypothesis, which is the 0.53. Do they give us an x and an n? Well, let's see. They tell us that our sample size is 100, right? So that's 100. Do they give us what x is? Well, no. They actually gave us the sample proportion, right? They tell us from these 100 people, 45% of them would vote for the incumbent president. Okay, so they actually gave us the sample proportion. So this is an example where they actually give us a sample proportion, and our calculator does not actually accept sample proportions. It only accepts x's and n's. Okay, so we have to back into this x somehow. Well, by using this formula, right? So this formula tells us that if solving for x, x is equal to p hat times n. So in our case, p hat is 0.45, and the n here was 100. Right, so that must be 45. Now, if this number actually did come out as a whole number, and if it doesn't, make sure that you just round this to the nearest whole number, because the TI calculator does not accept non-whole numbers for x's and n's. Right, and the function in our calculator is 1 prop z-test. Now, again, you can put all these values into this formula and you should be able to get the z-score. But in order to get the p-value, you can still use that z-score with the a normal CDF to calculate the p-value, which is going to be a two-tailed test. But this function in your calculator, the 1 prop z-test, just does all that for you. Okay, so let's go ahead and go to the calculator for this. Okay, we're here on the calculator. Let's go to stat. Let's go to test. we're going to go to one prop z-test. P with the little 0 next to it, that's just the proportion from the null hypothesis. So in our case, it's 0.53. X in our case is 45. N is 100. The alternative is that P is not equal to the value in the null hypothesis. So make sure that one's highlighted. So it's blinking on it. So make sure you press enter. Now that's highlighted. And let's go ahead and calculate. The outputs here are going to be our test stat and also the p-value for step 4. Okay, so our test stat is negative 1.60 and our p-value is 0.1090. Okay, so that's complete step 3. Again, in step 4, our output from the calculator told us that the p-value is equal to 0.1090. I usually round to 4 decimal places, but in reality for the p-value you just need enough decimal places, or at least one more decimal place than the significance level, because in step 5 we're going to compare these two numbers. So you want to round accordingly to make that determination. We're going to draw a picture in step 4. What kind of graph is this? Well, the test set reveals that for us, right? We have a z-score, so these are standard normals, normal distribution. And we have 0 at the center. And our test stat here is negative 1.6, so that's to the left of 0. Now, how many tails do we have? Well, the alternative tells us that. If it's a not equal to, that means it's a 2-tail test. So we also need the opposite of negative 1.60, which is on this side. And the area in these two tails, well, what's the area of that? Well, it turns out to be the p-value. So now this particular problem, the p-value is very close to the alpha, right? The p-value is still greater than alpha, so we're not going to be able to reject the null hypothesis because it just doesn't make the cutoff. Step 5, we're going to make our decision. Decision is made by comparing your p-value to your significance level, which in our case is 0.1090, 0.10. This is greater, so fail to reject. The null hypothesis. Do not reject. Okay, in step 6, let's see if we can logic our way through without the flowchart, but I'm still going to go to the flowchart. Okay, so the claim was the null hypothesis, right? We failed to reject the null hypothesis. So in a sense, we're accepting the null hypothesis. And if we're accepting the null hypothesis, then we have essentially found evidence to support this claim. Okay, so there's essentially not enough evidence to reject this claim. Okay, so let's go to the flowchart for the wording. Okay, so in our case, the claim was a null hypothesis, so we go this way. Did we reject the null hypothesis? No, we did not. So there's not sufficient evidence to warrant rejection of the claim. And then we restate the original claim. Okay, and the claim statement here is, again, it's nice that we highlighted it. Well, this is it's kind of spread out here. I would say the percentage of Americans who would vote for the incumbent president is 53%. So I'll write it that way. Okay, problem 9. This is more of a bare bones example. That just means that it's very straightforward. Okay, so it just says, use a significance level of alpha equals 0.05 to test the claim that mu equals 32.6. The sample data consists of 15 scores for which x bar is equal to 42.5. That's the sample mean. And the sample standard deviation S is 5.9. Okay, well, we always want to highlight the claim statement. And in this case, the claim statement is very simple. It's literally just claim that mu is equal to 32.6. That's it. Okay. So we start where we always start, our hypothesis statements. And this is a claim on the mean. And our claim statement suggests that it's equal to 32.6. That is the claim statement. And the opposite of that is that it's not equal to 32.6. Our significance level here is that alpha is equal to 0.05. Step 3 is our test stat. Test on one population mean. Again, there is a formula for this. It's x bar minus mu over s over square root n. Okay. Again, this value, the sample mean is coming from our sample data, and the mu comes from the null hypothesis. So again, these test sets are essentially measuring a difference between what we see in real life and what's being hypothesized. Mu, we have x bar, we have sample standard deviation, sample size. These are all going to be the inputs for our calculator. And of course, you can always plug these into your formula and calculate the test stat, the t-value. But the real advantage of using the calculator is that it comes up with the p-value. All right, so what's our mu? Well, that comes from the null hypothesis. That's 32.6. X bar, that comes from what's being given to us, 42.5. S is 5.9. And there's 15 scores, right? Okay, they're claiming that it's 32.6. Our sample suggests that it's 42.5. And the spread isn't that large, you know. So I'm going to say that, I mean, just by looking at these numbers, I'm going to I'm more inclined to say that this mean is not close to the 32.6, and especially since the spread isn't that large either. The 5.9 isn't that much of a spread. Okay, so let's see. So let's go to the calculator. So we have the blank home screen here. If you go to stat, go to test, t-test. We do have stats, so make sure you're under the stats menu. If you had data, then of course you would go to data and then enter a list. But we have stats. The mu from the null hypothesis, 32.6. The sample mean, 42.5. Sample standard deviation is 5.9. Sample size is 15. And the alternative here is a not equal, so that one's highlighted. And press enter. Again, the outputs here are our test stat, which is about 6.50 if we're just rounding 2 decimal places. Our p-value starts with a whole number, so you know that probabilities are always values are between 0 and 1, so it can't be a whole number. So that immediately tells us that to look to the right, and this is in scientific notation. So there's about 4 zeros in front of that 1, so it's 0.000014. Okay, so it's a very small chance of us being wrong in the case that we reject the null hypothesis. P-value is 1.40 times 10 to the negative 5. Again, if you wanted to have a decimal equivalent to that, you just move the decimal 5 places to the left, and you get 0.0000140. So that's a very small p-value. T-distributions have a bell shape. 0 is at its center. Okay. 6.5 is way out here. It's a two-tailed test given by the alternative. So we also need the negative 6.50. Okay. And the area in these shaded regions is the p-value. So it's that. That's a complete step 4. Again, we're going to make a decision in step 5, and the decision is made by comparing your p-value to your significance level alpha. And the p-value is well, I'll just write the scientific notation just to be a little bit more concise. That's definitely less than our significance level of 5%. Okay. So we are going to reject the null hypothesis. Again, the significance between the p-value is that represents the probability of committing a type 1 error. What's a type 1 error? It's when we reject the null hypothesis when it's actually true. Okay. So if we reject the null hypothesis, the probability of it actually being true is this small probability. Okay. We're comfortable with rejecting the null hypothesis because there's such a small chance of us being wrong in that decision. So that's our decision. 6, our conclusion statement. And again, the claim was that the null hypothesis was that mu was equal to 32.6. We rejected that, so essentially we reject the claim that it is 32.6. Okay, so let's go to the flowchart for that wording. All right, and so in our case, the null hypothesis was the claim, so we're going to go in this direction. Did we reject the null hypothesis? Yes. So the wording for the final conclusion is there is sufficient evidence to warrant rejection of the claim that, and then we would just restate the original claim, which in our case was just that it's mu equals 32.6. Okay, next problem. We're still dealing with hypothesis tests on one population. A manufacturer uses a new production method to produce steel rods. A random sample of 17 steel rods resulted in lengths with a standard deviation of 4.7 centimeters. At a 10% significance level, test the claim that the new production method has lengths with standard deviations less than 6.0 centimeters. Which was the standard deviation for the old method? Now, in all these problems, I am skipping all the conditions. Of course, for this type of problem, if we're dealing with a claim on a standard deviation, you have to know that the original distribution has to be normally distributed. But things that are manufactured typically follow a normal distribution. So let's go ahead and identify the claim statement. If you read through this, the claim statement is right at the end. It says, test the claim that the new production method has lengths with standard deviation that is less than 6.0 centimeters. The new production method has lengths with standard deviation less than 6.0 centimeters. So that's the parameter that we're talking about, a standard deviation. So step 1 is our hypothesis statements. The parameter that is in question is the standard deviation. The null hypothesis is always a statement of equality. And in this case, the claim statement suggests that the standard deviation is less than 6.0. So that would be the alternative here, 6.0. And that is in line with what is stated in the claim statement. And in the null hypothesis, this number has to match that, so 6.0. That's a complete step 1. Step 2 is our significance level. In our case, they tell us that it's a 10%. Step 3 is our test step. With dealing with a standard deviation, the test step for that is a chi-squared distribution. So it's a chi-squared test statistic. So it's n minus 1 times sample standard deviation squared over the population standard deviation squared, which again, this is essentially a ratio between what we see in real life from our sample data and what is being hypothesized from the null hypothesis. Now they give us all these pieces, right? They give us what S is, they give us what sigma is, what N is, right? S is the sample standard deviation. So if we reread this from a random sample of 17 rods, so that's actually our sample size, 17, the rods had a standard deviation of 4.7. So this sample had a standard deviation of 4.7. And the sigma here comes from the null hypothesis, and that is that it's 6.0. All right, so the claim is that the true standard deviation is less than 6.0. our sample suggests that it's 4.7. So far so good, right? We're in that direction that it's less than 6.0, but unless we actually do the test and come up with the p-value, we don't know for sure. Now, if you are using a TI calculator and you happen to have this function in your calculator, which is the math 200b, you would then use infer about sigma, and then we would test that sigma is less than some constant. So again, if you don't have this in your calculator, there's a workaround. What we'll do is we'll just actually calculate this test set, and instead of using that program, since you might not have it, we're going to use chi-squared CDF in our calculator. That's going to be under the distributions menu. So I'll show you how to use it. All right, so let's go ahead and just calculate this value by just plugging all the values in. So n minus 1 is 17 minus 1, which is 16. S squared would be 4.7 squared over sigma squared, which is 6.0 squared, or just 6 squared. And let me go ahead and calculate that. And I get something like 9.82 if I'm rounding, but I'm going to retain more decimal places just because I am going to use the function on our calculator, so I don't want to round too early in my problem. So 17778. That's fine. Okay. All right, so that's a complete step 3, but to come up with that p-value, I am going to use the chi-squared CDF. So I'll do that in step 4. So we have our p-value, and if I'm just drawing the picture here, chi-squared distributions are skewed to the right, so they start off at 0, and this test stat, well, a 9.81777. Well, how do I know to what side of this peak is? Well, the 50 percentile is typically around a little bit to the right of the peak, where the left-hand side of this dotted line represents 50% of the area, and the right-hand side is another 50%. Okay. In order to figure out where this test set of 9.8 lies, there's a couple ways to do that. Usually if it's less than the sample size, like 17, then it's to the left of this peak. And if it's greater than 17, it would be to the right of that peak. That's one way to do it. The way that I suggested before is if S is less than sigma, then this ratio of S over sigma is a smaller number, which is closer to 0. So you would see that here's 0. So that means if this value is less than sigma, then it's going to be somewhere around here, our test set. If S is greater than sigma, it's going to be it's going to be further away. It's going to be a much larger ratio, so it's going to be further away from 0, so it should be around here. Okay, so in our case, our S is less than sigma. All right. So our test stat is going to be around here, I would say. All right, so this partition is, again, 9.8177778. And to come up with this p-value, we're going to use chi-squared CDF. And the inputs here, if I have space, are lower, upper, and degrees of freedom. Okay, those 3 inputs. The lower value of the shaded region is 0. The upper is our test stat, 9.81778. Degrees of freedom is n minus 1, which in our case is 17 minus 1, which is 16. And this will give us our p-value. So let's go ahead and calculate that on the calculator. All right, we have our home screen cleared out. Let's go to second distributions. It's the vars button. And we're going to look for chi-squared CDF, not PDF. We won't use the cumulative distribution function. So press that. The lower value in this case would be 0. The upper would be that 9.8177778. Degrees of freedom, I said, is 17 minus 1, which is 16. paste, enter. I get 0.1240. That's a complete step 4. So that one was a little bit more involved if you didn't have that Math 200B program, but it's not too crazy of a process. Step 5, we're going to make our decision. The decision is made by comparing your p-value to your significance level. Okay, the p-value is 0.1240. Significance level is 10%. Again, this is the probability of committing an error if we reject the null hypothesis. A 12.4% probability of committing an error is too large for our tastes, because we were only willing to make that decision to reject the null hypothesis if the probability of being wrong was less than 10%, which is suggested by the significance level here. Okay, so we're going to fail to reject the null hypothesis. Step 6 is our concluding statement. Let's see if we can logic our way through. The claim was the alternative. We were not able to reject the null hypothesis, so in a way we can say that the null hypothesis is still true or accepted, so there doesn't seem to be sufficient evidence to support the claim. So we can go to the flowchart for that wording. All right, so in our case the claim was the alternative hypothesis, so we're going to go in this direction, and we were not able to reject the null hypothesis, so we failed to reject it. So the wording of our final conclusion is that there is not sufficient sample evidence to support the claim that, and then we would just restate the original claim statement. And the original claim statement was, the new production method has lengths with a standard deviation less than 6.0 centimeters. All right, next problem. It's hypothesis testing on 2 populations, and given the context of the problem, you'll have to figure out if this is dealing with proportions, means, matched pairs, or standard deviations. A marketing survey involves product recognition in New York and California. Of 558 New Yorkers surveyed, 193 knew the product, while 196 out of 614 Californians knew the product. At a 5% significance level, test the claim that the recognition rates are the same in both states. Okay, so where's the claim statement? Okay, well at the very end they say test the claim, and followed by the claim statement that the recognition rates are the same in both states. Okay, so is this a proportion? Is this a mean, a standard deviation? Are we measuring something? What's happening here? Well, a rate. A rate is something per something, right? So that's a proportion, right? It's how many people recognize this product out of those who were surveyed, right? So this is dealing with a proportion. So let's start where we always start. Step 1 is our hypothesis statements. And we are dealing with a proportion, okay? But we're dealing with 2 different populations, right? The populations that we're dealing with is New York and California. So I can call New York, I'll label that with 1, and California 2. The null hypothesis is always a status quo statement, right? So we just say that both states have the same exact recognition rates as one another, okay? Until there's evidence to suggest otherwise, okay? And the claim statement here says the recognition rates are the same. So the claim is that they are the same. Okay, to be the same means that they're equal. So this is actually the claim statement. And the opposite of equals would have to be not equal. So this is going to be a 2-tailed test. Okay. Step 2, we have our significance level. I believe it said it was, what, 5%. Step 3 is our test stat. Our test stat for a 2-prop z-test, it's a pretty long formula. You can look it up on the notes, but it is a z-score. So I'm just going to write z equals. Okay, and the function in our calculator that we're going to use is, well, we're dealing with two populations, so it's going to be 2 proportion, 2 prop z-test. Okay, this is going to give us a test stat or z-score and also the p-value. Okay. And what are the inputs here? Well, the inputs are going to be essentially your sample data for each population. So since we're dealing with proportions, they're going to be x1, n1, x2, n2, right? 1 is for New York, and 2 is for California. So let's see if we can identify all these pieces from the problem. So if we reread this, it says 558 New Yorkers surveyed. So that's how many New Yorkers were surveyed. And 193 recognized the product, right? And 196 out of 614 Californians knew the product. Okay, so 614 is the sample size, and only 196 actually recognized this product. Okay. And I'm kind of curious, what would be P1? That's x1 over n1, right? And then P2, just to kind of give you an idea of what these values were. So in this case, it was 193 over 558, 196 over 614. This is just extra information. Okay, so that was just for my own understanding. This is approximately 34.6%. This is approximately 31.2%. The claim is that these are exactly the same, right? Of course, from sample to sample, we don't actually have access to all the population data, so we can't really see if these are exactly the same. But we're going to be able to see if they are significantly different or not. All right, so let's go to the calculator for that. Okay, we're here on the calculator, blank screen here. If we go to stat, we're going to go all the way to test, and we're looking for 2 prop z-test, 2 proportion z-test. Okay. All right, so there's your x1, n1, x2, n2, and then whatever our alternative says. Okay, so let's just go ahead and type those away. This is a two-tailed test, yes. And let's go ahead and calculate. All right, our test stat is 0.968 if we're rounding. You only really need a couple decimal points here, but 0.97, I would say. And the p-value is, it's pretty high, 0.333. Okay, since we're dealing with a test stat that is a z-score, z-scores are bell-shaped. We have 0 at the center. Okay, and where would be a 0.97? Well, 0.97 is to the right of 0, so it should be somewhere around there. It's almost a standard deviation away. And we know it's what, a two-tailed test? Yeah, because of the alternative. That's telling us there's a two-tailed test. So to have another value on that left-hand side here, and because of symmetry, we have a negative 0.97 here. And the area in these two tails here is a sum total of 0.333. So there's about like 16 point something percent area in each one of those tails. Okay. Even if it was just a one-tailed test, 16% wouldn't be less than your 5% significance level. So still wouldn't be able to reject the null hypothesis. All right, so that's a step 4. Let's go to our decision here. Decision is made by comparing your p-value to your significance level. What's the p-value? Well, in step 4 was 0.333. Significance level in step 2 was what? 0.005? 0.05. And of course the p-value is greater, so we're going to fail to reject. Again, what is this whole decision about? A p-value is the probability of rejecting the null hypothesis when the null hypothesis was actually true. We don't want to make that mistake, so we want to limit that to up to a 5% chance of making that mistake. That's what that significance level represents. The fact that we calculated there being a 33.3% chance of us making that mistake, that was a little too high for our taste, really. So we're not going to make that decision to reject. So we're failing to reject. That's the idea behind that. Conclusion statement. Well, let's see if we can logic our way through this. We failed to reject the null hypothesis. So in a sense, we're saying that the null hypothesis is still true. So let's go up to our step 1. If the null hypothesis is still true, so that lines up with what the claim is. Okay, so the claim is essentially accepted in a way. Obviously, you don't really accept things unless you have access to all the population data. But for now, there's not enough evidence to reject the claim that P1 is equal to P2. So let's go to the flowchart so we can get the correct wording for that. All right, so what was the claim statement? Well, that was in the null hypothesis. So we're going to go up here. And did we reject the null hypothesis in step 5? Nope. So we say that there is not sufficient evidence to warrant rejection of the claim, and then we restate the original claim statement. And what was the original claim statement? Well, if we look at the highlighted sentence, that the recognition rates are the same in both states. Let's go to the next question. Here's another hypothesis test on 2 populations. Again, there's keywords in the problem that will indicate whether we're dealing with a claim on a mean, proportion, or a standard deviation, or matched pairs. 2 types of flares are tested, and their burning times in minutes are recorded. Use a 5% significance level to test the claim that the 2 samples are from populations with the same mean. The summary statistics are given below. Okay, so they just kind of give us a nice, neat list of statistics from the sample. Okay, so we have 2 different flares that are being tested. We have brand X and brand Y. I'll give them better labels. I'll call this 1 and 2. And we're trying to see if what? Well, let's highlight the claim statement. Test the claim that the 2 samples are from populations with the same mean. Okay, so what they're probably trying to say is maybe these 2, even though they're 2 different brands, are probably being manufactured by the same company, so they're just relabeling them. And that's essentially the claim, that they're probably exactly the same. Just by looking at these, there's 35 here, 40 here, so about the same sample size. But on average, these were 19.4 minutes of flare time, and this were 15.1 minutes. Again, just comparing averages isn't enough. You have to compare the spread. The spread, well, it's not spread out that much. The data is pretty compact within 1.4 minutes, right? That's a measure of spread, and this is about 0.8, so that's not spread out that much either. Just by looking at that, I'm going to go ahead and guess that these are significantly different, just by looking at the spreads here and how far apart these means are. It doesn't seem like there's a lot of overlap. So that's essentially the way you want to kind of conceptualize these. I mean, of course, if you have a whole list of data, it's hard to actually have that type of intuition, but that's just the kind of thinking I want you to apply here. Okay, so let's actually continue with the test to see if I'm right. Step 1 is our hypothesis statements. And again, we are dealing with having the same mean. Okay, so we're comparing the mean in one population is the same as the mean in the second population. That's always our null hypothesis. We always assume these are exactly the same until we have evidence that suggests otherwise. And does that line up with our claim statement? Yeah, they said that that's the claim. So again, this is the claim statement. Okay, the null hypothesis isn't always the claim. Okay, I know it seems like it is in this practice exam, but if you want a more variety of examples, look at the questions in your notes in the previous sections. So the opposite of equals is mu1 is not equal to mu2. Step 2, I can fit this in right here. What's our alpha? I believe they said it was what, 5%? Step 3 is our test statistic. Our test stat is, well, when comparing 2 population means that are independent, we are using a t-test. Okay, there is a large formula for this. I'm not going to write it all out, but on our calculator, it's going to be 2samp t-test. It's good to know the formula just so you can identify what is needed. So you should know what that is. But if you just go to 2sample t-test, it'll list out everything that's required. Okay. And what are those? Well, it's going to be x1 bar, s1, n1. So that's for the first population, right? That's brand X. And then there's also the same stats for the second population. So I do see it listed above, but I'm just going to rewrite it over here. That way I have it in the correct order that our calculator wants it. That way I don't mix these numbers up. That's another common mistake. People mix these numbers up. All right, let's go to the calculator. All right, we're here at the cleared out home screen here. Let's go to stat. We're going to go to test. Look for our 2sample t-test. There we go. Do we have data or stats? Well, we have statistics, right? They did all the dirty work for us already. If we had data, then we'd go here and have to plug in everything to a list. But we have stats. All right, let's go ahead and type in all our inputs here. So just make sure that you double check before you go on and press calculate. The alternative here was that mu1 is not equal to mu2, so keep that highlighted. For these types of problems, we're always going to have pooled no. Okay. The pooling has to deal with assuming that the population and standard deviations were the same. There was nothing to suggest that. And in my class, I don't go over questions like that. So this is a more conservative test. And then we're going to calculate. Okay, the test set comes out to be pretty large, 16.02. Again, you can think of that as number of standard deviations from the mean. It's pretty far off, right? It's not exactly that interpretation because we're talking about the t-distribution. But you can definitely see that by looking at the p-value. See how it starts off with the whole number 7? You know, p-values are probabilities, so that means you have to look all the way to the right. And yeah, you see that? e to the negative 22. That means there's 21 zeros in front of that 7. I'm not going to even try to expand that. It's a very, very tiny number. Okay, so we're definitely going to reject the null hypothesis because the probability of us being wrong in our decision to reject the null hypothesis is very, very tiny, to the point where we're very comfortable rejecting the null hypothesis. That was a complete step 3. Here's p-value. It is 7.35 times 10 to the negative 22. I'm not going to bother expanding that at all. That's a tiny number. Okay, very small probability. What shape do we draw? Well, t-distributions are also bell-shaped, so they are centered at 0. Our test stat of 16.03 is way out here. We know this is a two-tailed test because the alternative is not equal to. We also need the 16.03. And the area to the left of that and to the right of the right one. The sum total is this p-value. That's a complete step 4. Step 5, we make a decision. The decision is made to reject the null hypothesis by comparing the p-value to your significance level alpha. The p-value is 7.35 times 10 to the negative 22, which is much less than 0.05. So we're definitely comfortable in rejecting the null hypothesis because there's a very small chance of us being wrong in that decision. And in step 6, well, what was our claim statement? Well, we rejected the null hypothesis, which is the claim, right? So there is sufficient evidence to reject the claim that the two samples are from populations with the same mean. So, like, I interpreted this as them saying they're probably from the same manufacturer, but this clearly states that they're probably manufactured completely different. So let's go through that flow chart and get the correct wording for this. Okay, so the original claim was in the null hypothesis. Were we able to reject the null hypothesis? Yes. So the wording of the final conclusion is there is sufficient evidence to warrant rejection of the claim that, and then we just restate the original claim. And what was that original claim? It was that the two samples are from populations with the same mean. All right, next question. again, hypothesis testing on two populations. Assume the two dependent populations have been randomly selected from a normal distribution. Okay. 10 different families are tested for the number of gallons of water a day they use before and after viewing a conservation video. At the 5% significance level, test the claim that the mean is the same before and after the viewing. Okay, so the situation here is that there's 10 families. Each family has been given a conservation video to watch, so I guess the benefits of conserving water. And they're seeing their water consumption before that conservation video was watched and then after, okay, to see if there was any difference between a before and after, right? Because that's what the claim statement is. Claim that the mean is the same before and after viewing. So they're suggesting that even though they watched this conservation video, then their habits aren't going to really change. That's the claim. That's exactly the same before and after. Okay, so let's go ahead and look at our data here. We can see that each one of these is a family, right, before and after. So there's 10 pairs. And you can see in this particular case, that first family, they consumed 33 gallons before and then 34 after, so they didn't really change their habits. The second family here, it looks like they did reduce their amount of water they use. Third family did also, and there was mostly reductions, except here it's exactly the same. 35 and 33, a little bit of a reduction there. There's a pretty big reduction here, pretty big reduction here. These people didn't care. They just kept on. They increased their water consumption here. Okay, so let me just erase that. So this is a before and after, and these are matched pairs because we're dealing with the same family. Okay, so the values from this data set are directly related to values in the other set because it's the same exact family. Okay, so what we analyze here are essentially the differences. Okay, and we'll call that lowercase d. And let's go ahead and take the difference. Now, in some cases, you might want to subtract in one way rather than the other, depending on your hypothesis statement. So let's go ahead and actually come up with that first, okay? Because if it's a one-tailed test, like a left-tailed test or a right-tailed test, you might want to subtract in a certain order. Okay, if it's a two-tailed test, it doesn't really matter because for two-tailed tests, because of the symmetry, you'll have a test stat to the left of 0 and the test stat to the right of 0, and it'll be exactly the same. So let's see if that's the case here. Okay, so we have the null hypothesis and the alternative hypothesis, and we are having a claim that the mean is the same before and after, or we say that the mean difference is 0, right? That's what it is in the null hypothesis. Okay, for two things to be exactly the same, that is the exact same thing as saying the difference between them is 0, right? And that, yeah, that lines up with the claim, okay? And the alternative is that it's not equal to 0, that it's something other than 0. So it's either their consumption went even more, or it was reduced. That's what the alternative here suggests. All right, so let's go ahead and calculate the differences here. And since it's a two-tailed test, it doesn't really matter the order that you subtract, okay? So that's what I'm going to do in this case. I'm just going to subtract before minus after. So we'll have a -1, and over here we'll have 5, and I'm just going to keep on going for the rest of these. Okay, so that is the list here of differences. And what I like to do is just put in the differences into a list here. And just by analyzing the data, just by the looks of it, if the difference was 0, like as the claim statement suggests, then these should average out to something close to 0. I see a lot of large positive numbers that don't get offset by a lot of large negative numbers. So I don't think that the difference here on average is 0. But again, I can be wrong about that. We'll have to actually conduct the actual t-test here in order to make that determination. So step 2 is our significance level. Alpha is, in this case, 0.05. And let's go to step 3 here, our test stat. Okay, so to test a claim on the mean difference, it's going to be a t-test. It's just going to be a simple t-test because we essentially reduced this from 2 populations down to really just one list of differences. Okay. The formula for this, just so that you recall, is the average of our differences divided by the standard deviation of the differences divided by the square root of n. Okay. Now we do have a list of data, so we'll have to put in those values in a list in our calculator and then calculate this test out. But I do want to actually have the calculator output these values. Okay. This essentially would be like our x bar, and this will be our sx. Okay. We do know what the n is. That's the number of pairs of data, or essentially the length of our difference list, which in this case, there were 10 families. Okay. Let's go to the calculator. Okay, we're at the blank home screen. We're going to have to put this data into a list. Let's go to Stat, go to Edit, and I'll go ahead and clear out some of these lists here. Okay, now that that's cleared out, let's go ahead and enter their data. Again, for the negative values, make sure you're using the negative symbol and not the subtraction symbol. The negative symbol is right below the 3. It's in parentheses there. So make sure you do that. Otherwise, you'll get an error. Okay, now that your data is all in there, always make it a habit to check your inputs. My inputs look like they're good. So I'm going to go ahead and back out of this by pressing second quit. I'm going to go to Stat, go to Test, and this is just a simple t-test. Okay. We treat this as if it was just one list of data. And we're only analyzing the differences here. We're not under stats, we're under data, so make sure that that's highlighted. And the value in the null hypothesis, well, the mean difference is 0, so just replace that with 0. The list, my list was in L1, so just keep that at L1. If that says something different, just press second 1, of course. Frequency, just leave that at 1. And the alternative is that it's not equal to 0, so yeah, not equal to. Let's go ahead and calculate this. All right, our test set is 2.89 when rounded to 2 decimal places. Our p-value is 0.018 when rounded to 3 decimal places. And our x bar is 4.8. That's just the mean differences. That's our d bar. And the s is 5.24. I'm just going to list those out, even though they're not really necessary. But I'm going to list them out on my page here. All right, let's complete step 3. Step 4, the p-value from the previous output. If you go back to that calculator, it came out to be 0.018 when rounded. And what's the shape of our graph? Well, we're dealing with the t-distribution, which we know is bell-shaped. The 0 at the center. 2.89 is out here. And a negative 2.89 would be out here because we are dealing with a two-tailed test. Now, if you had subtracted in the opposite direction, if you did after minus before, what you'll end up having is everything would have been negative. It would have been a negative 2.89. So either way, you'll end up having this exact same picture because you'll have to have to write the positive 2.89. So the p-value is this area in these two tails, and that is smaller than our significance level, right? That's about 1.8% versus a 5%. So in our decision, whether we should reject the null hypothesis, that's done by comparing the p-value to our significance level, p-value being 0.018, significance level being 0.05. The p-value is less than, so we are comfortable in rejecting the null hypothesis because the probability of us being wrong in that decision is smaller than what we were willing to be wrong, which was a 5%. 6, we're going to come up with our conclusion statement. We rejected the null hypothesis, and our claim was the null hypothesis, so there is sufficient evidence to reject the null hypothesis. So again, let's go through that flowchart to get that wording. The null hypothesis was a claim again. We rejected the null hypothesis, so the wording here is there is sufficient evidence to warrant rejection of the claim that, and then we restate the original claim. And the claim was that the mean is the same before and after the viewing. All right, last question. There is a small typo I need to fix. We're talking about a supermarket, but I say bank here. All right, a local supermarket claims that the variance of waiting time for its customers to be served is the lowest in the area. Okay, the variance just is a measure of spread. For something to have a low variance means it varies less, right? Which means it's very predictable. A competitor supermarket checks the waiting times at both supermarkets. The sample statistics are listed below. Test the local supermarket's hypothesis. Use a 5% level significance. Okay, so they're giving us some data here. So at the local supermarket, there was 13, customers, and the standard deviation of these 13 waiting times was 0.99, okay? The competitor, they measure 16 customers, and the sample standard deviation of those 16 customers' waiting times was 1.17. Now, what was the claim statement? Test the local supermarket's hypothesis, and what was that? The local supermarket claims that the variance of waiting times for its customers to be served is the lowest in the area. So if it's the lowest in the area, then it's lower than any competitor. Okay. So far, just by looking at these two numbers, these standard deviations, 0.99 is less than 1.17, right? So far, so good. But we're going to test to see if they're significantly lower. Okay. And that's what we're going to do here. Step 1 is our hypothesis statements. This is a test on the variance. The variance is a sigma squared, right? So sigma squared, it could be a test on the standard deviation. It's the same test, okay? So it doesn't really matter. The null hypothesis is always a statement of no change or equality, right? Status quo. So population 1 has the same standard deviation as population 2. And we'll call local supermarket to be population 1 and the competitor to be 2. Okay. And the claim statement suggests that the variance at this local supermarket is the lowest in the area, so that means it's lower than any competitor. So their variance is less than the competitor. That is the claim statement. So in this case, the claim is the alternative. This could look like it's going to be a left-tailed test. Step 2 is our significance level. Let's identify that. It looks like there's a 0.05. Step 3 is our test stat. So when comparing two standard deviations from two populations, we're going to be using a thing called an F test. Okay, and that test stat is actually very simple. It's just the sample standard deviation of population 1 squared divided by the sample standard deviation of population 2 squared, or the variance of sample 1 divided by the variance of sample 2, because that's what S squared is, variance. Okay. They give us sample standard deviation. They give us S1, N1, S2, N2, right? So this is for the local, this is for the competitor. And I'll just rewrite those values here, even though it's redundant, but it's fine. Okay, now you can actually just calculate this test stat here just by plugging in these two sample standard deviation values, but we really want to get the p-value out of this. Okay, so that's what the 2SAMP F test is for. 2SAMP F test. Now this formula doesn't require an N1 or N2, but in order to calculate the p-value, it does require it. That's one of the inputs. So let's go to the calculator for this. Okay, I add a blank home screen here. Let's go to stat. Let's go to test. And it's much easier if you go up, and you should be able to find it pretty quickly. 2SAMP F test. Let's go ahead and press enter. And do we have data? No, we have stats. So let's make sure that we scroll over to stats, press enter, and let's go ahead and fill this in. Okay, the alternative is that sigma 1 is less than sigma 2, right? So make sure that we scroll over that. So let's go ahead and calculate. And our test stat here is 0.72, if I'm rounding just to 2 decimal places. Our p-value is 0.283. Okay, so it's a pretty large p-value. Definitely not less than our significance level. Okay, so what about the picture here? So an F distribution, has a skew to the right distribution, so not bell shape. There's a vertical axis, horizontal axis, starts off at 0, and it peaks somewhere here, and then it has a long right tail. It goes on forever. Okay. Now this test set of 0.72 has to lie along this x-axis here. And how do we determine? Well, again, if S1 is less than S2, then this ratio is pretty small for the test set, which makes it closer to 0. So you'll see that your value would be somewhere around here. If S1 is greater than S2, then this ratio for the F test is a large value, so it should be further away from 0, so probably to the right of that peak. So in our case, S1 is less than S2, so we have this situation. So our test stat here should be somewhere around here, I would say, 0.72. And this is a left tail test because the alternative says less than. So we shade to the left. And the area of that shaded region is the p-value. Okay. And of course, you can also say, well, if this is a left tail test, we can position that 0.72 in such a way that when we shade to the left, that shaded region should represent about 28%. All right, that's a step 4. Step 5, we make our decision. And how is this decision made? Well, just like always, we compare our p-value to our significance level, p-value being 0.283. Our significance level was in step 2, 0.05. And the p-value is definitely greater than the significance level. And we're going to fail to reject the null hypothesis, because if we reject the null hypothesis, the probability of us being wrong in that decision is 28.3%. We're not willing to take that risk because we were only willing to take a risk up to 5%. So we're not going to reject the null hypothesis. So the conclusion here is, well, we failed to reject the null hypothesis, so in a way we are accepting the null hypothesis. Not really, but in a way. And if we're accepting that, then there isn't sufficient evidence to support the claim that sigma 1 is less than sigma 2. Okay, so let's go ahead and look at the flowchart for that wording. All right, so in our case, the claim statement was the alternative. And we were not able to reject the null hypothesis. So we say there is not sufficient sample evidence to support the claim that, and then we just restate the original claim. And the original claim was that the variance of waiting time for its customers to be served is the lowest in the area. Okay, that's it. Thanks for watching.